We meet in an hour of change and challenge, in a decade of hope and fear, in an age of both knowledge and ignorance. The greater our knowledge increases, the greater our ignorance unfolds. Man in his quest for knowledge and progress is determined and cannot be deterred. The exploration of space will go ahead, and it is one of the great adventures of all time.
Welcome to the panel discussion at TechNiche 2021, the annual Techno-Management Festival organized by IIT Guwahati on our topic, the Cosmic Saga, the origins, evolution, and eventual fate of the universe. In 13.8 billion years, our universe has undergone an enthralling evolution from a tiny speck to the immense wonder it is today. From blazing stars and ginormous galaxies to the smallest life forms and modern technology, it all arose from a single point in an infinitely dense universe. Embedded in this remarkable history are tantalizing clues to a new and more powerful understanding of the reality we live in. Today, humanity has reached a stage where we can finally search for these clues in our biggest experiments. Our panelists today are scientists and experimentalists at the forefront of this quest to understanding our reality and what may lay in the future of our universe. Please allow me to introduce our panelists. Our first panelist is Dr. Viatcheslav Mukhanov, the scientific director of the Journal for Cosmology and Astroparticle Physics. Our next speaker is Dr. Chris Parks, the leader and spokesperson of the LHCb Experiment at CERN, the organization that operates the largest particle laboratory in the world. Our third panelist is Dr. Puragra GuhaThakurta, the chair of the Department of Astronomy and Astrophysics at UC Santa Cruz. Our moderator, Dr. Nirupam Roy, is an assistant professor at the Indian Institute of Science in Bangalore. As a final reminder to our audience, we also have a Discord server where you can watch and discuss this discussion with friends and fellow enthusiasts. We'll be running a Q&A session at the end of the discussion, so if you have any questions for the panelists, feel free to put them in the chat box below. All right then, without further ado, let's head right on to the panel. Over to you, Nirupam sir.
Thank you very much, Srishti, and welcome to the audience who have joined this program, which I am very certain is going to be a very exciting 1.5 hours ahead of us. My job here is to sort of moderate the whole thing with a very minimal intervention. But before we go into that discussion, let me just quickly tell you about our panelists today, who will be talking about this cosmic saga. Now, of course, when we talk about cosmic saga, you know, the cosmos is all that is, was, or ever will be, as Carl Sagan has put it. And 1.5 hours is sort of really very, very short time to even start to discuss the origin, evolution, and the eventual fate of the universe, the topic of today's panel discussion. However, we will try to see what we can go through within this limited period of time. And as the organizers have managed, they have got 3 stars here for us today, 3 stars from 3 different fields, from cosmology, from astrophysics, and from particle physics. And they will today be sharing their thoughts and comments about this cosmic evolution with all of us. You know, so I sort of want to start with this quote from Neil Gaiman, He wrote, a philosopher once asked, are we human because we gaze at the stars, or do we gaze at them because we are human? Pointless, really. Do the stars gaze back? Now, that's the question. And for the audience today, you know the answer to that. We have got 3 stars for you in the panel today to sort of talk to you about all this, right? The people who we have in the panel today, let me just briefly introduce them for you. We have Professor Mukhanov from the Ludwig Maximilians University at Munich, also known as the University of Munich or LMU. He is the chair of cosmology at the Arnold Sommerfeld Center for Theoretical Physics, leading the group of the theoretical astroparticle physics and cosmology there. He has done really impactful and groundbreaking work which help us understand the formation and evolution of the structure in the universe and its relation with initial quantum fluctuations. I will not go into the details as he himself will be telling us about it later, but I must mention that his work in this field, particularly the 1981 work and the later follow-up works, are milestones in theoretical cosmology. Professor Mukhanov did his PhD from the Moscow Institute of Physics and Technology. And after that, he was at the Institute of Nuclear Research in Moscow and then in ETH Zurich for the period of 1992 to 1997. And 97 onward, he is at LMU. His research interests are inflationary models, cosmological constant, dark energy, classical and quantum physics of black hole, quantum cosmology, and string cosmology. He has developed this quantum theory of cosmological perturbations in generic inflationary model. Professor Mukhanov is recipient of numerous awards, including the Gold Medal of the Academy of Science of the USSR, the Oscar Klein Medal, the Gruber Prize in Cosmology in 2013, the Max Planck Medal in 2015, the ICTP Dirac Medal, and so on. He has also received the Chair Blaise Pascal, a prestigious distinction awarded by the French government, the Tomala Prize by the Swiss Tomala Foundation for Gravity Research, and the Amaldi Medal of the Italian Society of General Relativity. As Srishti already mentioned, he also works as the scientific director of the Journal of Cosmology and Astroparticle Physics, created by the International School for Advanced Studies, or CISA, and he is author of an excellent and extensive treatment on the physical foundations of cosmology. Very warm welcome to Professor Mukhanov as one of our panelists.
Thank you.
We also have in our panel Professor Christopher Parks, who is Professor of Experimental Particle Physics at the Department of Physics and Astronomy, and working in the particle physics group at the University of Manchester, UK, and also at CERN. Again, as Srishti has already mentioned, he is the spokesperson of the LHCb Experiment at CERN LHC and leads the UK participation in LHCb, including the LHCb upgrades. Professor Parks did his BA from the University of Cambridge and DPhil from the University of Oxford. And then he was a CERN fellow for the period of 1998 to 2000. And then he has worked with a PPARC fellowship at the University of Liverpool. He has worked at the University of Glasgow for the period of 2002 to 2011, and 2011 onward, he is at the University of Manchester. He has also been a CERN scientific associate for the period of 2010 to 11 and 2018 to 19, and a guest professor from 2020 onward at CERN. He has done groundbreaking work related to the W mass measurement group on the Delphi experiment with Large Electron Positron Collider LEP. He was the project leader of the LHCb Velo project, the Vertex Locator project, during the first LHC physics period 2010 onward. He has been awarded the Institute of Physics High Energy Physics Group Prize in 2010. His research focus is new physics through the study of matter-antimatter asymmetry and development of radiation hard detectors. And of course, the very crucial role of the LHCb spokesperson for the collaboration, which is, if you just look at the number, it's just amazing. More than 1,400 collaborators from 85 institutes spread over 19 countries. And he will be talking to us more about this during the course of this event. So a warm welcome to Chris.
Many thanks.
We also have with us Professor Puragra GuhaThakurta, Professor and Chair of Department of Astronomy and Astrophysics from the University of California, Santa Cruz. Professor GuhaThakurta did his PhD from Princeton University in 1989. And then he was at the Institute of Advanced Studies, followed by Hubble Fellowship from 1992 to 1994. Then for a short period, he was at STSCI. And then from 1994 onward, he is at UCSC. Professor GuhaThakurta is very actively involved, apart from his being the professor and chair of the Department of A&A, is also very actively involved in the SPHERE program, supporting the early research exposure to high schoolers, as well as the UCSC Science Internship Program. Professor GuhaThakurta has received many awards and honors, including the NRC Canada Hodgepog Memorial Prize and the Alfred P. Sloan Research Fellowship. He is closely involved in the upcoming 30-meter telescope, or TMT. He is currently a member of the International Science Definition Team of the TMT. His research interests include formation and evolution of galaxy, exploring this aspect by using sort of the local fossil galaxies as well as directly looking at the distant galaxies. And again, he will be telling us more about that during the panel discussion today. But apart from this identity, Professor GuhaThakurta, and here I should probably say Raja GuhaThakurta, is also an eminent artist, specialized mostly in oil and pencil works. He has received many recognitions and awards for his work in that field as well. So a very warm welcome to Professor GuhaThakurta.
Thank you.
So with this introduction, I think we sort of will move to the discussions now, which the way we have planned is that our panelists will start with a brief presentation on this theme about today's discussion, and then we'll come back to the discussion again. Professor GuhaThakurta, maybe if we start with your points and opinions on this topic, and you can tell us about the galaxies.
Can you see my screen share okay now?
Yes, we can.
Okay. Yeah. Thank you very much for that kind introduction, Nirupam and Srishti. So I'm going to say a little bit about galaxies. This is a topic I've been studying for many years now. And I'll briefly touch upon subtopics that involve galaxies, cannibalism, dark matter, and really how dark matter in the Milky Way, the fact that our Milky Way is a dark matter-dominated galaxy, how that is related to the origin of the periodic table of elements here on Earth, and so related to life on Earth. One of my more unusual stints has been being on sabbatical at Google. That was something that happened 6 years ago now. I just want to mention that. So I'm grateful to my home institution, UC Santa Cruz, but also to Google for helping me with some of the work I'll talk about. I thought that a talk on galaxies should start with a picture of galaxies. Here's a picture of my favorite galaxy in the whole world, the Andromeda Galaxy, and some of its companions. You can see one of its companions right here, just to the upper right of the nucleus of the Andromeda Galaxy. These are the same image, but shown at 4 different contrast levels. This is a digital mosaic, and at the time, this was these images were put together. At the time, it was the first digital image mosaic of the Andromeda Galaxy. It was put together by 3 of my colleagues, Shomak Chaudhary and I, took the images at the telescope, but 2 students, Andreas Berlind and Phil Choi, did the difficult work of stitching the individual images together into this mosaic. The images were taken in 2 filters, in blue light and infrared light. And this was over 30 years ago that we did this work. And it really started me on a journey to understand this large neighboring galaxy of ours. We live inside a galaxy and we can't see it from the outside. We don't have a long enough selfie stick to take a picture of the Milky Way from the outside. So this is the next best thing. We can look out of the many windows we have in our own galaxy, and we can look at our neighbor, the Andromeda Galaxy. This is the largest galaxy it's the nearest galaxy that's bigger than our own. And so I grew completely fascinated with it. And in this image here, you see the Andromeda Galaxy. It's this little speck. If you can see my cursor, it's this little speck that's just a little bit lower and to the left of the center of this panel. And what we're going to do is we're going to zoom into this image of Andromeda. And this time we'll use a different mosaic, one taken with the Hubble Space Telescope. And the galaxy, Andromeda Galaxy, is about 2.5 million light years away. And this arc of light and darkness, stars and dust, is the arc of our own Milky Way galaxy. So we literally are looking out of one of these windows at our neighbor's house. And fasten your seatbelts, because we're going to fly at an unrealistic speed towards the Andromeda Galaxy, a virtual journey towards Andromeda. So I'm going to remove the label so it doesn't distract from the movie itself. Again, as we zoom in, we'll see the companions of Andromeda. You can barely see there's a dot just sort of above it. That's one of the companions. This is another companion down here. So as we zoom in, you'll start to see the details of the Andromeda Galaxy. The individual stars, gas and dust, dark nebulae that make up the Andromeda Galaxy. At this point in the movie, you should be able to see individual points of light. These are individual stars in the Andromeda Galaxy, color-coded by the way they would appear to our eyes if our eyes were sensitive enough and had sharp enough vision to see this. This is a segment of an actual Hubble Space Telescope image, a color composite of many filters. The Hubble images were taken in 6 filters, 2 ultraviolet filters, 2 visible light filters, and 2 infrared filters. But this is an mind-boggling level of detail. The way I think of this is, imagine, flying over a beach. If you're in India, let's say you're flying over Juhu Beach near Mumbai, and you've got a window seat. You look out of your window seat and you take a picture of the beach below you. But imagine your camera has high enough resolution that you can see the individual grains of sand. Well, that's what this image would be. You could see all of the Andromeda Galaxy, but you can also see the individual points of light that make it up. So our team is using this to study many aspects of the Andromeda Galaxy. And one of the things we're studying is how collisions between galaxies have shaped galaxies like Andromeda and our own. Now, collisions take a long time. And I just calculated, when you said that the universe started 13.7 billion years ago, to compress all of that story into today's 90-minute panel requires a compression factor of about 10 to the power 14. In my idle few minutes before this panel started, this is what I was calculating. So you're seeing a highly compressed history highly sped up history. And I'm going to speed it up here too by showing you computer simulations of what happens when galaxies collide. So when galaxies collide, here are two frisbee-shaped galaxies. Their mutual gravity causes them to orbit around one another. But in this particular simulation, these two galaxies are about to collide. And you're seeing now two real galaxies that are about to collide. I've gone from the computer simulation back to a real image, back to the computer simulation. As these two galaxies start to intersect each other, these computer simulations of galaxies, as they start to intersect each other, we stop the computer simulation briefly, change our perspective. And here's a second pair of galaxies that are intersecting in the process of merging. Back to the computer simulation, tidal forces start to rip, each galaxy starts to rip the other one apart. And here's a real pair of galaxies that are going through that process. The central bodies of the galaxy start to fall back together as a few stars carry away a lot of energy from the system. Stars get orphaned from the system. And here's, as we change our perspective and pause the simulation, here's a real pair of galaxies going through this collision. So galaxy collisions are spectacular. They're all around us. They take a long time to unfold, so we can't follow any single system collide during a human lifetime. But through simulations like this, and by stitching together sequences, you can see what happens to galaxies as they collide. Now, this is all fine, and you might be sitting there thinking, how does this matter to us? It matters to us because we know now that the Andromeda Galaxy is headed for a collision with our own galaxy. So here's Andromeda again. Here's the Milky Way galaxy. And what you're about to see is sort of a little bit of fantasy of what our Andromeda Galaxy might look like in the future as our mutual gravity brings the two systems together, So this is today. A few billion years from now, Andromeda will look bigger. They say astronomers wondered why Andromeda was getting bigger and bigger, and then it hit us. In about 4 billion years, there'll be a collision. And these are real images of colliding galaxies that are used to create this sort of fantasy of what our future will look like, our galactic future will look like. Our future as a planet won't be threatened by this collision. It'll be threatened by other things, like the sun becoming a red giant. But without thinking about that morbid future too much, let me talk a little bit about our past. And this is my last slide. Our place in the cosmos, our place on Earth, the place of, when I say our, I mean, this is my son lounging on the carpet, so dogs, even the simple deadly coronavirus, humans. What connects us all is our complex chemistry, made up of protein molecules, DNA, RNA. These molecules have many chemical bonds in them. And to form multiple chemical bonds, you need elements in the periodic table that are deep inside the periodic table. You can't do this with just hydrogen and helium, which are the elements that are synthesized naturally shortly after the Big Bang. So these elements that I'm talking about, say carbon, nitrogen, oxygen, they're abundant here on Earth. And they're abundant in our parent star, the sun. But one of the great mysteries initially was that how did the sun get to contain these elements when it didn't actually produce them through nuclear fusion reactions? The answer to this question, did the sun produce these elements, these atoms, their nuclei? The answer is no. The sun acquired these atoms from the nebula in which the sun and solar system were born. These elements were seeded by previous generations of stars, the sun's ancestors. Solar ancestors came in many sizes and masses, and the massive stars are the ones that went through rapid nuclear fusion relative to the sun, rapid. They ended with explosions that had two functions. The explosion produces elements heavier than iron in the periodic table, and also has the effect of dispersing this as stardust through our surroundings. And it's out of this stardust that our solar system was born. And it's because of this that our planet has the elements to support life. Now, for this, we had to be part of a galaxy because we needed to have other stars around us. And most importantly, we needed to be part of a galaxy that has so much dark matter, so much gravity, that these powerful explosions of stars were reined in by the gravitational potential. If we were living in a smaller galaxy, less massive galaxy, these supernova explosions would carry the material clear out of our galaxy, and the next generation wouldn't benefit from it. And we can see this very clearly when we study chemical abundance patterns in galaxies. So I'll stop here and hand you back to Nirupam, and I will stop screen sharing.
Thank you very much. Amazing, isn't it, that the details, I mean, on one hand, when most of us, I mean, at least earlier when I used to think about the cosmos, the sky, everything, as if everything is like well controlled, right? Simple things moving around each other and the galaxies far away from each other and so on. And here you are giving us a picture which is a lot more violent, galaxies which are colliding and a lot of things happening triggered by that. And it seems very, very wild and chaotic. And of course, this is what leads to the overall evolution of the galaxies through the cosmic time, right? So I want to ask one thing at this point to you, Professor GuhaThakurta. See, all these studies, whether observational or numerical simulation, they talk about dark matter, and it's, of course, I think one topic which our audience, they want to know more about it. We call it dark matter. What all so far is known about it, and what are the unknowns, and what are the directions in which scientists are progressing to know more about it? So can you tell us something more about the dark matter component of the galaxies?
Well, my fellow panelists know a lot more about the physics of dark matter than I do. I'm a poor astronomer. All I can tell you is that it exists and how much there is and how much it costs. No, I can't tell you how much it costs. I can tell you how much it costs to study it. But I do want to emphasize that the evidence of dark matter, as mysterious as it sounds very Harry Potter-esque, right? Our universe is being, it's a tug of war between two dark forces, dark energy and dark matter. It sounds very mysterious, but I do want to say that all of this is based on evidence. It's based on evidence that, Vera Rubin studied how rapidly galaxies were spinning. She studied the very Andromeda Galaxy. I was fortunate to have her as one of my mentors. She studied how rapidly something was spinning, and she applied very simple principles, Newtonian gravity, v squared r divided by g to within some to within a factor of order unity gives you the mass of a system. If you take the rotation speed of a planet, the orbital speed of a planet around the sun, that v, if you square that, multiply by the radius of the orbit, and you divide by the gravitational constant, that gives you the mass of the central object whose gravity is causing that planet to be in an orbit around the sun. Applying very similar principles, you can, if you measure how rapidly a galaxy is spinning as a frisbee, if you measure how rapidly the Andromeda Galaxy is spinning, what Vera concluded was it was spinning at about 250 kilometers per second. This is the speed at which stars were moving. And it was roughly constant as a function of radius. That really was the surprise, the fact that it was constant, because if you measure the run of m divided by r within a galaxy, just based on the stars it contains, you would expect the rotation speed to be falling, reaching a maximum and then falling, because as you step further and further out, you accumulate more and more mass, but m over r is dropping. So m over r is directly related to v squared. So if m over r is dropping, v squared should also drop like square root of m over r. V should drop like square root of m over r. And what she found instead was it was flat. This whole mystery of flat rotation curves, it wasn't a subtle effect. You expected it to drop from 250 to 80 kilometers per second. And what she saw instead was something steady at 250. So there was about 10 times as much, a factor of 3. So you have to square that for its implications on mass. There was about a factor of 10 more mass than you would deduce just by looking at the light of stars. To me, this was a pivotal moment in astronomy, where you discovered that something as beautiful as a galaxy, something that we live in and rely on for our chemistry, it's actually, its gravity is dominated by something we can't see. We can't see it, but it exists. And it makes its presence felt not through interaction with light, not by emitting light or absorbing light, but by exerting gravity. So it's ordinary matter in this sense. It's nothing exotic. It's not as exotic as dark energy, but maybe I should, it is exotic in some senses of the word, but it's matter. Its position in Einstein's equations of general relativity is just where stars and planets would fall. It's no different from that. Sorry, that's a very long answer to the question you ask about dark matter. It's very evidence-based. It's very strongly evidence-based.
Sure, yeah. And since you also, pass it on to other panelists, part of the question, I will come to Professor Mukhanov about, maybe a bit of provocative question here. I mean, apart from all this body of observational evidence that point to the existence of dark matter, last few decades, there also have been development in the theoretical side regarding alternative explanations, right? Many of these has been phenomenological. Some of these has been, digging deeper into alternatives to our current understanding of the theory of gravity and so on. So what is your take on this? I mean, this whole body of work about the alternative explanation of dark matter-like phenomenon.
What do you mean alternative explanation? Because there is only two possibilities. Either there exists unknown particle or there is some kind of modification of the gravitational equation. Mm-hmm. If you do very simple modification, for instance, like adding this mimetic matter or whatsoever, then it's okay. Yeah, you understand. It's like particles also. But you understand that dark matter, of course, was discovered in gravitational interactions. When people say that it was not discovered or indirect evidence, it's completely wrong. It was not discovered in the other interactions. Now, what is the fundamental structure of this thing? Of course, we do not know. This is the reason why it's good to make experiment to find out it's new particle or not new particle. But on the other hand, it exists, it's there. Okay, if you start to make ugly models or ugly modification of Einstein equation to explain one number, then it's not worth doing it, as you understand, because theory should not just explain something, but it should also predict something, you see? And here, with all these super ugly models, like Hardensky gravity or whatsoever, I do not see what you can win compared to the elegant general relativity, you see? Mm-hmm. But you can write new papers on this subject. This is one of the outcomes.
Okay, I see. And also with, part of this question, I will come to Professor Chris Sparks. So regarding the detection of the dark matter, right? Of course, we see these evidences from astrophysical observation, not just in the galaxy rotation curve, but from many other things. Even the large-scale structure, its details will depend on how much of dark matter is there. The galaxy cluster scale, we have evidence of the existence of this component. But probably the smoking guns evidence, we expect it will probably come from some particle physics experiment. Maybe you can tell us briefly about the current status and what are the things which are happening in this direction from a particle physics perspective.
Absolutely. I mean, as Professor Mukhanov was saying, if indeed it does have a particle origin, then of course it is an open question for particle physics as to whether that dark matter particle can be observed. There's a whole range of different searches that can be done for dark matter, and it depends upon the technique that you might want to use will depend upon the mass that you assume for the dark matter particle. The status in brief is that there have been lots of searches for dark matter particles and we have not seen any. now, picking up exactly on what Professor Mukhanov was saying, you would like your theory and your model to have predictions. So what would be wonderful is if, speculating, you were able to find a particle that was able to explain not only this huge area that we do not understand of dark matter, but was also able to explain some other mysteries of our fundamental particle physics. Then it would be extremely powerful, because it would really try to tackle the problem of putting the large-scale universe that we are primarily discussing here today together with the fundamental particles of which the universe is made. And really, there are two main ways in which the dark matter is searched for in particle physics experiments. It can be searched for in looking for the interactions of the dark matter particles, such as Raja was talking about, just the ones which are in the galaxy halo, and they could pass through our detectors and we could observe their interactions with the detectors. Or you can take the alternative approach where you really try to directly produce the dark matter particles, and in particle physics collider experiments, you actually produce a new particle which could be the dark matter candidate, or could be related to the dark matter candidate, and then try to directly observe those in the experiments.
Mm-hmm. Yeah. Okay. Yeah. Thanks, Professor Parks. And I am thinking that even if we will come to the questions from the audience at the end of this panel discussion, there are a couple which are sort of directly relevant, and I think maybe we can take some of those. For example, here is a question from Anirudh, who asked that it is said that iron is the most stable element and cannot be fused further inside the core of the star. How is it that we can find heavier elements on Earth? So, Professor GuhaThakurta, maybe.
Sure. Yeah. So iron is indeed the most stable nucleus. So beyond that, fusion reactions are, endothermic. That is, you put in a certain amount of energy. You have to put in a lot of energy in any case to make fusion work, because these particles that you're bringing together are positively charged in the nucleus, bringing together, say, an alpha particle with an existing nucleus. So you need very high temperatures, high speeds of these particles, so they can sort of, against the Coulomb barrier, they can still approach each other close enough. I'm talking about things in classical terms, but they can get to a point where the strong nuclear force can start acting. And by its very name, you know that the strong nuclear force only operates over very short distances. So you need very high temperatures to make this happen, even for exothermic fusion reactions coming up to the element iron. What happens beyond that just cannot happen within the normal confines of a star. There's not enough energy available to create heavier elements through the normal process of fusion. What happens instead is more energetic phenomena, and neutron bombardment is needed to push an upward cascade beyond iron. You capture a neutron, and when iron captures a neutron, it goes up in atomic mass, not in atomic number, and then through beta decay, something can go up in atomic number at fixed atomic mass. So this alternating neutron capture and beta decay can cause this upward cascade beyond iron. And when stars explode, what happens is the inner parts of the star collapse into becoming neutron rich. They become neutron stars or black holes. But there's a lot of energy available. You don't care. The system doesn't care that it's going to undergo something endothermic. There's a lot of energy available during the explosion. There are a lot of neutrons available, and that's where this upward cascade happens. Not just in stellar explosions. We now understand that in certain late stages of stellar evolution, like the asymptotic giant phase, you can have slower neutron bombardment, but the S process and R process are good at producing elements that are heavier than iron in the periodic table.
Mm-hmm. Yeah. Okay. Thank you. So I think we will gradually move to the earlier universe now from this point. So next, I will request Professor Chris Parks to share with us something about his work, more related to now breaking up the stars and galaxies into even more fundamental units, and telling us about the matters in the universe and antimatters which we mostly don't see in the universe, and why this type of injustice to the antimatter exists in our universe. Professor Parks.
Many thanks, Nirupam. Can you see my slides okay?
Yes, yes, yes.
Perfect. Okay. No, many thanks for the kind introduction. So yes, as Nirupam said, I'm going to talk a little bit about this from a particle physics perspective, with a particular emphasis on antimatter. So it's really a great pleasure to be invited here. I'm sorry that we cannot be together in person in India. I really love my visits to India. I think the last time I was there was probably about 5 years ago now. In fact, I managed to find a photo of myself at a conference we had at TIFR in Mumbai. It's a shame that unfortunately we can't be there together. But let me tell you a little bit about the work that we are doing. So the Large Hadron Collider, which is at the European Centre for Nuclear Research, but in fact, really these days it's a really international facility, is on the French-Swiss border close to Geneva. And it's the most powerful particle accelerator. The particle accelerator itself is 100 meters underground, and it's 27 kilometers in circumference. And protons go around this circle in both directions, and they are collided at 4 points around the circle, which are the named ones here. And that is where the 4 large experiments of the Large Hadron Collider are. The one that I work on is the Large Hadron Collider Beauty Experiment, LHCb. What we know from really 50 years of knowledge of particle physics and of the fundamental particles now is that we have this theory which is called the standard model of particle physics. And this describes all the fundamental particles that we know about. And these are captured in this diagram on the left-hand side. So a couple of remarks on this. First, you see that there is this kind of mirror symmetry here between the ones which are called particles and the ones which are called antiparticles. So this thing is a topic we haven't brought up yet in our discussion today. For all the particles that we know about, there are equivalent antiparticles. And these particles come in 2 types. They come in quarks. The quarks form together to form particles such as the proton and neutron, of which we are all made. And also leptons, which include the electron, for example, which you're familiar with, no doubt, because it's also a primary constituent of our atoms. And that captures really what we know about our fundamental particles. They are accompanied by force carriers, and these force carriers are force carriers of 3 of the 4 fundamental forces of nature. We were just talking about the strong force. There is also the weak force responsible for nuclear radioactive decay. There is the photon responsible for electricity and magnetism effects, electromagnetism. And in recent years, a few years ago now, in the first run of the LHC, at the Large Hadron Collider, we discovered the last particle in this standard model, which is the Higgs boson. But you will see that there are some major emissions that this model does not explain. So one first obvious one is that it only explains 3 of the 4 forces. And of course, the big scale, large scale discussion that we have just been having is dominated by gravity, which is not in this picture at all. You will also see that there is a symmetry here between matter and antimatter, between particles and antiparticles. This basic picture looks very symmetric, but yet our universe today consists entirely of matter. And as we've just been discussing, there is this unknown quantity, as just discussed, for which there is really superb evidence astrophysically, dark matter, but for which there is no known particle physics origin. If we go back to the Big Bang, our primary understanding, our best hypothesis for the Big Bang, that equal amounts of matter and antimatter would have been produced. But yet, here we are, nearly 14 billion years later, and we have undergone this evolution of the universe, forming our basic particles from the quarks, the protons and the neutrons, forming our nuclei, forming our atoms, forming the stars, and ending up with the universe that we live in today, in which the universe today is entirely dominated by matter. So we start, we believe, in a symmetrical situation of matter and antimatter, and we come today to an entirely matter-dominated universe. And exactly the way in which this matter in antimatter imbalance arises is still a major puzzle in physics today. I mean, one thing we do know from our experiments over the last, indeed, 50 years, and a number of these new types of matter-antimatter difference have been discovered at the LHC in my experiment over the last few years, is that there is a fundamental difference between matter and antimatter. If you go back to the original origins of the idea of antimatter, and Dirac wrote down, well, even before Dirac, there were speculations by Schuster, Professor of Physics from my own institute, University of Manchester, at the end of in the 1890s, and then through to the 1920s, Dirac wrote down an equation which had two solutions to it, both a matter and an antimatter solution. And all those early work was really symmetric between matter and antimatter. And then in the 1960s, first fundamental difference was observed between matter and antimatter. And we have managed to embed this inside our standard model picture. We've managed to embed a difference between the behavior of matter and antimatter. So for example, this is one of the measurements and discoveries that was made at my experiment. And we plot a particular particle decay as a function of the mass. And what we observe is that we see more of these particle decays into matter than the equivalent antimatter decays. So the equivalent particle and antiparticle do not decay to the same final state at the same rate. There is a fundamental difference between matter and antimatter. The problem is that while qualitatively that sounds tremendous because it explains or could potentially point us in the direction of this matter-antimatter imbalance in the universe, quantitatively, these differences that we observe are nowhere near big enough to explain the difference in the universe in which we live now, which is entirely matter dominated. And then at the LHC, we are producing a whole set of different probes. We can look for directly produced dark matter. We can look also for extremely rare decays of particles and look for unexplained phenomena in them. And many of you may have come across that we recently released a new result. Now, I guess about 2-3 months ago, I picked up one headline from Scroll.India, where it's somewhat hyperbolically described as potentially a new force. That's, I think, somewhat speculative. But what we did in this was to look for rare decay processes, in this case of particles containing the beauty quark, and about 1 in a million decays, they decay into this particular way that we're analyzing. And they should decay equally into 2 of the particles that we described before on this picture. You see that on this picture, there are the electrons and they are their heavier version called the muons. And we should have decays in which there are equal numbers of electrons and muons in the final state to which we are decaying. And what we see is hints, certainly not proof at this point, but hints of a deviation. In our scientific speak, it is known as about 3 sigma, 3.1 sigma. It's about a 1 in 1,000 chance that this could be purely by statistical fluctuation. It sounds small, but in our particle physics experiments at the LHC, we have put out well more than 1,000 papers in the last 10 years that we have been operating. But whether this turns out to be real or not, gives you an idea of the sorts of ways experimentally that we can try to get a view on this picture. These CP violation phenomena, these matter-antimatter phenomena, looking at the differences between matter and antimatter, or looking at these extremely rare processes and comparing them with the theoretical predictions. They are both ways that you can look for deviations in your fundamental theory, and they could point us to having to add new particles or new interactions to the theory. Brief summary, antimatter and matter are almost symmetric. Where all the antimatter that we believe was produced in the Big Bang went is still a fundamental problem in physics quantitatively. And the new discoveries that we could potentially make in particle physics experiments could illuminate other puzzles, such as, for example, the nature of dark matter. And it would be wonderful, of course, if some of these unanswered questions were related to each other, and then the new additions to the theory would be tremendously powerful because it would multiply solve problems. It would not be just adding one item to the theory to solve one individual problem, but having the power of really being able to significantly improve your theory and hopefully try to converge between these worlds, the very small of particle physics and the very large of cosmology.
Thank you, Professor Parks. So I think the first question that come to my mind when I see this presentation is that lot of this experiment, when we read about them as general public perception or even in the media, we come across things like, as you mentioned, this fifth force, in a similar line. For example, we have heard about LHC is going to create a mini Big Bang, right? Things like that, title like that. Now, my question is that, this standard model of particle physics has been a very successful model, matching things to the 5th, 6th decimal places, and so on between the theory and experiment. And yet, there are certain aspects where things are not matching, right? One of the things is, for example, this G2, muon G2 anomaly, which has come into the picture very recently, and so on. How much do we know about when we extrapolate our understanding of the standard model of particle physics and think about the very early universe scenario and so on? How much extrapolation is there in the question I'm sort of trying to ask is how much extrapolation is there, and how much similar is it? The experiments are to the early universe conditions.
Yeah, I mean, what we try to do really is understand the fundamental particles, their interactions between them. And really, we can probe the three forces that I was just discussing of electromagnetism, the weak and the strong force. You're right, you then have to make a link with the cosmology. Maybe one aspect I bring in as a slight aside is that there is a state early in the universe called a quark-gluon plasma. And that is one element that the research at the LHC, which I did not touch on in my presentation, is also trying to illuminate. One of the 4 experiments at the LHC, the experiment Alice, is particularly trying to understand the properties of this quark-gluon plasma, a state early in the universe. But then it also raises more fundamental questions, like I was discussing the differences between matter and antimatter, and I was discussing them in terms of quark interactions. But we do not know that those quark interactions are in any way necessarily related to the basic matter-antimatter imbalance in the universe. It could be in a completely different sector. It could be, for example, as a result of lepton interactions. There are really very many things we do not know here. What I think we have the power of is that we have these experiments now which move us into a different realm from what we have explored in particle physics before. The energy of the LHC, the pure rate of interactions of the LHC, so the quantity of data being much higher. And we hope through that, that maybe we can start to open a little window, and through that window we can make links. Exactly as you were discussing, the other, in addition to our lepton flavor universality that I was just discussing, the other big anomaly that came up during the spring is the magnetic moment of the muon from an experiment at Fermilab. And there are theories that try to tie these two phenomena together. And they do so by potentially adding new particles or new interactions to the standard model. One possibility is adding particles or forces which interact both between the leptons, the particles like the electron and the muon, and the quarks, these particles that are forms of part of the protons and neutrons, with so-called particles or forces called leptoquarks. But there are many speculative theories in this area, and it will be very intriguing to see whether any of these anomalies really persist, and if they could potentially be related to each other in the future.
Okay. Yeah. So, Professor GuhaThakurta, I would like your comment on one question which I have on the chat from Ranjan, who asked, why does the antimatter have to be symmetrical with the matter? And I think because I want, this question comes to you in the sense as a broader question. Earlier, Professor Mukhanov also mentioned in the context of the alternative gravity theories, whether some theories are ugly and some theories are, more beautiful, right? And of course, your great grand supervisor, Chandrasekhar, wrote a whole treatise on it, the book Beauty and Truth, right? About the, this thing that scientists inherently look in a theory or in whatever they're modeling and so on. And you are also, in addition to being an astrophysicist, but also an artist. So what is your take on this thing, this symmetry that we look for, this connection, that beauty that we look for? Is it really there, or is it just our perception and we just put our own sense of beauty, or something we find that this is beautiful, but this is not, and this is a symmetrical thing is more beautiful, otherwise it is not, and so on. What is your take on this?
I will say that the Mona Lisa is not looking straight at the artist in that portrait. Her face is tilted. It's the lack of symmetry that makes the universe beautiful. I'm a firm believer in that. Now, to come back to your first question, I mean, the E equals mc squared inherently has particles, and when you go from the E to the M, if you go from the left-hand side of the equation to the right-hand side of the equation, you're taking a pair of photons and you're producing a pair of matter and antimatter particles. That's, so to answer your first question, this is why you expect them to be present in equal numbers. I mean, this is the production that Chris talked about at the Big Bang. This is how you expect particles to be interchanging between particle form and photon form. And so we expect the process to be entirely symmetric, and whether we are all living a quantum fluctuation or not is how I was taught to understand the baryon asymmetry in the universe, the matter-antimatter asymmetry. But again, the panelists are far greater experts than I am, but I can just say in art, it's not the most symmetric painting that's the most beautiful, not at all. If you look at all of the great masters and all of the wonderful paintings they've produced, it's the blemishes, it's the innovation, it's the interesting things about the paintings that make them what they are, not pure symmetry, never pure symmetry.
Okay. Professor Mukhanov, would you like to add something to this? Sorry, your microphone is mute.
Okay, I can just add very nice story from Kabbalah. I got it from the friend of mine, Francois Englert. Okay, but I thought that for me, it's more relevant than for your breaking of conformal symmetry. And the story is the following. It's Kabbalah story. I can give even reference. So when God was borrowed to be alone, he decided to create something nice. But first problem with which God faced was that God was everywhere. There was no place to create something. Then God found the solution. God shrank to the point and created universe outside, expanded and found himself or herself, whatever you want, in extremely boring universe because it was the most symmetric. Nothing was happening there. Then God thought a little bit, okay, and before shrinking, he distributed a little bit garbage around. Then, when he expanded back, he discovered that he lives in a nice evolving universe. And the whole idea is presented there in the following way. Only by breaking divine configuration, they can be perfected. You see? So, violation of the symmetry is a basic thing in the physics. You see, otherwise it's some kind of boring mathematics. And in physics, you can never say beautiful or not beautiful. In real physics, it can be true or not true. And true or not true, you decide with experiment. When there is no experiment, there is no physics.
Understand. Yeah. Okay. I think so. This may be the right time to move to the third part of the panel discussion and going back to even more earlier universe where we don't even probably worry about matter, antimatter, anything else. There are only quantum fluctuations. I don't know the details, but Professor Mukhanov will tell us about it.
Okay, so let me share the screen. Okay, 1 minute. Wait. So you see, actually, what I want to tell you that in extremely early universe, the only thing which was playing very essential role was gravity. Particle physics was relevant, but not up to such extent as most of the people think about it. Zeldovich, one of my teachers, was telling that universe is accelerator for poor people. I could say today that for extremely poor people, you see, because what is relevant for gravity normally is pressure and energy density. And right now you see two pictures. It's not Hollywood, it's two real pictures. One picture is the picture of the hydrogen atom taken with electron microscope. Yeah, sorry. Okay, so let me go back. Okay, on the left, and it refers to the scale 10 minus 8 centimeter. The other picture is the direct photograph of the universe when it was much, much younger than right now, because now it's 13.7 billion years. But this picture is direct photograph of the universe when it was only 300,000 years old. It's young, but not too young, because at this time, we already know all physical laws in the universe. How we managed to get this photograph? We used for this cosmic microwave background, which is everywhere. If you look at the darkest point in the sky, you could not expect that it's dark, because photons, microwave background radiation, comes from the most darkest part of the sky. There are about 400 photons of this radiation per each cubic centimeter. And the basic thing that this photon decoupled from the rest of the matter at the time when the universe was 300,000 years old, still baby universe, and after that, they were not scattering. You see, it's like delayed photograph. And, okay, you see here different colors, but different colors are some kind of embryon from which galaxies after that will originate as a result of gravitational instability. Okay, the main principle, which you know, rich gets even richer, poor gets even more poor, as you understand, yeah? So the parts where there was a little bit more matter bring more matter, and then it becomes very complicated physics, I would say astrophysics, yeah? But right now, what you see, it's still in linear regime where physicists can apply their methods and can make calculations. You could ask me, okay, 36 orders of magnitude, what is behind of these two pictures? What they have in common? And what I will try to show you, that we have solid experimental proof that behind of both of these pictures is the same very elementary formula, which is called Heisenberg uncertainty relation, and which is basis of all quantum theories. If you know this formula, and if you are a good student, after you took course in classical mechanics, the rest of physics you could derive as a home exercise. Hard exercise, but nevertheless it's derivable, because in this formula there is everything. You could ask, okay, how it can be? Okay, atom, I understand, it's very small, and here there is Planck constant. But the other thing refers today to the scale megaparsecs. But you shouldn't forget that universe is expanding. And what we have today on the huge scales, when you trace it in past, all the galaxies, all the matter which we have in the galaxy were within some very little volume, which is smaller than 1 centimeter. You see, all this huge amount of matter was in extremely small box or ball, if you want to say. And then you could think that in this case, maybe quantum mechanics could be important. And in fact, it happened like this one, because I came in the field of cosmology in 1980, when there was no experimental data practically, there were astrophysical data, and cosmology, what I would call, was not physics, it was not natural science, it was natural philosophy. You see, but as a student, you don't care about experiment, you care mostly what your advisor will tell you. And I happened to be in the right place, in the right time, which was a little bit before, and we addressed the following question. Okay, everybody already in the 80s knew that the universe which you observe when it was 1,300,000 years old should be not very boring. There should be some little inhomogeneities, okay? The amount of matter in different places here on this picture should vary by the fraction of the percent, 1,000th of the percent, okay? Nobody has seen this picture at this time yet, but people were thinking that it should be like this one, because otherwise you would never understand how galaxies are originated. And everybody, of course, thought that universe is expanding. It was one of the beliefs, okay, which had solid experimental justification. And then this time, okay, with my collaborator, we thought that maybe this origination of this picture, where you see clearly the embryos of the galaxies, could be referred to extremely early moment of time. So from 300,000 years, you have to go to the time which is 10 minus 36 seconds after creation of our universe. So universe was huge at this time, extremely small, and you could think about quantum fluctuations. Now, okay, what is quantum fluctuations? Quantum fluctuations, you know very well what is this. It's the thing which is due to the uncertainty relation. If you would consider, for instance, electron moving around nuclei, this electron has two possibilities: either to emit radiation and finally collapse in the center, yeah? Otherwise, iPhone would not be working. Or, okay, what to do? It could emit nothing. iPhone are not working, but then matter would be stable. So you needed to decide between stability of matter and your iPhones. I do not know what you would prefer right now, okay? iPhones or death. But you know that Heisenberg resolved this problem because he found the way how to reconcile iPhone with the life. And it's quantum mechanics, because according to quantum mechanics, okay, electron is emitting radiation, but unless it comes too close to the nuclei, and after that, this Heisenberg uncertainty relation do not allow it to get in the nuclei and to end up the life. Okay, so we use these minimal fluctuations, okay, which tells that there is no absolute rest in the world. Used after that earlier very useful stage of dark energy, which is called inflation right now, and then produce some theory which had perfect predictions. You see, one simple assumption: universe is accelerating, quantum fluctuations, and 4 unbeatable predictions. Namely, that you have to get universe which at the present moment of time has Euclidean geometry, then I do not go to the detail. Adiabatic perturbations, which were extremely unpopular at this time because Jim Peebles was fighting with them, telling that they are not in agreement with astrophysics. It should be Gaussian, most simple embryons without extra features. And the most amazing thing, actually, which we were able even to calculate the spectrum of fluctuation, which happened to be not one, I mean, not flat, not scale invariant, etc., but there was small deviation from scale invariance, because the number 1 is natural number, but you could ask where number 0.96 comes. It's non-trivial number. How could you build it? You see, by the way, we know that, for instance, at birth, the ratio of girls to men is precisely 0.96, but up to now, nobody has any idea why it's so. But in cosmology, we know why it should be 0.96, because this deviation from n equal 1 is determined by the logarithm of the ratio of galactic scale, megaparsec, to few millimeter scale, which is a typical wavelength of the background radiation. So this follows from formula which involves both Planck constant and gravitational constant. There is other formula like this one, like temperature of Hawking radiation, but it was never checked. Now, what about 0.96? Of course, in the 80s, nothing was known, etc., but using this prediction, nevertheless, you can recalculate the things, what you have to see as a difference of the temperature on the sky, and you would get this picture with this prediction, which would have only one parameter, namely the amplitude. You see, the rest, like Hubble constant, I can take from astrophysics. Otherwise, why do we need astrophysics for cosmology, right? Now, so this was prediction from 1980, which was, okay, difficult to imagine that it will be even verified. But cosmology as a real physics started in 90 with a lot of cosmic microwave background radiation measurement, yeah? And I will not go through all of them, so don't worry, there are hundreds of them. But I will go just through space missions. Yeah, so first, of course, it was discovered in 65, all this radiation. After that, there was COBE measurement, which found low resolution picture of all this inhomogeneity, slight variation of the energy density in the universe when it was 300,000 years old. Then there was a great experiment, also space experiment, WMAP, but all these experiments were beaten by so-called Planck experiment, which was 500 times more sensitive than WMAP, and it has resolution 3 times better than WMAP, angular resolution. Okay, so it was the device, it was collaboration, then you see how many people were in this Planck collaboration compared to WMAP collaboration. Everything is growing, price also has grown. And this is not Hollywood, but this is real launch of the Ariane, yeah, which brought on in the Lagrange point L2 two devices, Herschel, about which perhaps you never heard, and this Planck, where there was actually two instruments, high frequency instrument and low frequency instrument. But high frequency instrument was cooled also. He needed to be cooled. Okay. It was covering for 3 years. 5 times it covered the whole sky. Then you clean this sky from dust, from synchrotron, and the picture which you got is this brilliant picture after cleaning, and you can compare it with the previous experiment. Now, you take this map here, okay? Then you make statistical analysis of this map, and then you are getting from this statistical analysis this experimental data, right? Dependence of the temperature fluctuation from the angular separation of the between two antennas. And arrow bars here, by the way, at L equal to 1000, it's 4 times less than the size of the point. Don't think that actually there is no arrow bars. And then you compare it with one parameter theoretical prediction. Bingo. What could be better? But experiments were even more better because they could measure polarization of background radiation and compare with no free parameter prediction, you see, of the theory. And for this polarization, people got this kind of curves. Okay, red curve is a theoretical prediction, and the points are experimental data. From this data, by the way, you could measure the 2s hydrogen atom decay rate, yeah, with emission of 2 quanta with accuracy 5%, never reachable in any lab, you see. It's atomic physics contribution. Now, what follows from here? Of course, all these things which you know, this cosmic pi, I don't need to tell you, dark energy, dark matter, ordinary matter. Of course, people say that we do not understand most of the matter, but it's junk, okay? This most of the matter is just one parameter, okay? Forget about it. What is relevant for us? But look actually at this kind of things which you extract from this observation, and especially for this spectral index, okay, which was predicted to be 0.96. And here is the accuracy. Now the accuracy is 0.04%. So its deviation from the flat spectra at the level more than 8 sigma. You see? So, as Lyman Page wrote to me once when he has seen this thing in experiment, he told that his hair stand up. He could not believe it, that people will find this 4% deviation, which is nothing more than 2 divided by logarithm of galactic scale to CMB typical scale. So megaparsec divided by few millimeters, you see? And now what follows from here, I think actually is finished in this sense. The general relativity is valid up to the scale 10 minus 7 meters, which have accelerators, and all want 20 centimeters, yeah. Although on accelerators, we do not know physics above 10 minus 8. Gravity do not at this time. When you produce embryons for connected and they will produce at 10 minus 35 seconds at this moment, and after that they were sleeping up to the moment when the universe became 300,000 years old, woke up, and produced this nice picture. Anyway, in 10 minutes the talk, which normally I give within 1.5 hours. Hello.
Yeah, thanks, Professor Mukhanov. So, yeah, I guess I'm audible, right?
Yes, I finished.
Yeah. So, the first question that that came to my mind that I want to ask you, and I already see there are already a few questions of that line in the chat box, right? This particularly arises when there is mention of inflation and so on. But even I think there is a very basic question people ask, that universe is expanding. What is it expanding into? I think, if you want to take that question from one of our participants first. And a related question maybe that I have is, one prediction that comes from the standard model of cosmology that we have currently, the lambda CDM, including the inflationary scenario, is that one of its prediction is multiverse. Our observable universe is a very small patch, and there is a
multiverse. I am sorry, is not prediction. Multiverse cannot be checked. There is multiverse or there is no multiverse are two statements which are equally wrong or equally correct. Okay, you cannot speak about something as about prediction if it's in principle not possible to verify. Now, there is other more dangerous thing actually. Multiverse, if you produce a lot of other universes with the same property, you are still physicist. You can study, physics in each particular universe because they are very similar. But when people start to speak about landscape, about different kind of physics, then it becomes complete chaos. You can blah, blah, blah till infinity. And then you don't need even to explain anything because you could say that everything, what you can imagine was realized in one of these infinite number of universes. But I know how to change the theory to avoid this kind of landscape infinitely reproducing universe. It depends on the model. Don't tell me that, it's the killing consequence of this model that we are predicting God knows what. We are predicting very particular things which refers to the observable universe, which is, I think, large enough to be happy.
Okay. And, I don't really know how to take this question when lot of people ask this whenever they hear about the expanding universe, that what the universe is expanding into.
It's just expanding. What is the future of our universe? Nobody knows because it depends on the nature of so-called present dark energy. We have no even idea why do we need it there. Normally, I make actually semi-humoristic explanations that God decided to give us hint that such kind of matter can exist, which was extremely useful in the past when we were creating our universe, because using dark energy, production of the universe becomes like this one. You see, before that, it was a horrible headache, but if you use dark energy, you do not know how to stop to produce universes. Because, for instance, François Englert in one of the papers in 78 wrote that we should not overproduce the universes. Too many. I asked him, François, 2 is enough for you. You need 3 or 5. What does it mean? Or infinite number? You understand, the question is not in the number of the universes. The question is that if you are producing universes, if they have similar of physical quantities, okay, statistical quantities, then our job or our salaries when we study the universe are still a little bit justified. When you are producing God knows what, then, okay, it's not clear what we are paid for. You see, we have to go to the different department, philosophy or God knows what, yeah.
Okay, so this probably should, also take us to the direction of what is one of the topic of this panel discussion, the eventual fate of the universe. And you said it's very hard to say, but there are various scenarios which people predict, right? Short time scale, of course, short as in short compared to the cosmic time scale. There are some of the things which Professor GuhaThakurta mentioned. This evolution of galaxies, their mergers, eventually what is the fate of our solar system and the Milky Way. I guess the current galaxy evolution model predict that things will gradually move into more and more boring type of galaxies, right? The red and dead elliptical galaxies. And then what about the long-term thing? What are the possibilities?
Everything in our universe will die, you see, so this is a natural prediction about which nobody, okay, doubts. Not only people have finite lifetime, galaxies, stars, everything has finite time. On the other hand, I do not see a problem with it if universe, to produce universe is so easy. Why you have to care about this universe which is getting very, very old? You see, no problem. Because at the beginning, we could not imagine how to make universe like we see today. This was the reason for the appearance of this kind of anthropic principle, you see, about which before Hawking changed his opinion, he was telling, I cannot imagine that God fit parameters in a special way to create so horrible monkey like people. You see, politically incorrect statement, but it was 30 years ago, it was still possible to do it. You see, the anthropic explanation is not so-called explanation. As I told you, okay, beauty depends on the taste. Explanation of something is not yet explanation if it's not checked that it's really working thing. So-called prediction, at least one prediction, you see. Because if I will take any single fact, for instance, which people observed on LHC, this kind of 3 sigma anomaly, I am sure that people will easily write 1,500 papers, okay, explaining of this 3 sigma result. And as you understand, 3 sigma for particle physics is nothing. You see?
Yeah. So on a related question, I will come to Professor.
Maybe I comment on that. No,
Sure.
I was going to concur. 3 sigma discrepancies are known to come and go in particle physics. Absolutely. We really have to add extra weight to see what happens in the longer term. Indeed, I think our RK paper has more than 100 citations already, exactly proving. And what's really important is if people can make predictions which can actually be tested, not post-dictions, but predictions, where we can actually make experiments that can actually tie this together to make an explanation out of this, rather than being able to tweak the parameters in a model to be able to explain something that we see. And the intriguing thing is, if the range of anomalies that have been seen at the LHC and elsewhere, if these can be tied together inside a cohesive theory that we can check. Now, then that would have a lot of power.
Yeah. So the question with which I was sort of coming to you, Professor Parks, is that in this whole evolution of the universe, one of the key role is played by dark energy, the lambda, right? The first letter of the lambda CDM standard model of cosmology. Standard model of cosmology, I believe everyone will agree that it is nowhere close to the standard model of particle physics. So far, there are so many details to be worked out and so on, and the precision, etc. However, when we look at that lambda, I think there is a huge discrepancy there between our current understanding from the astrophysics and cosmology perspective. And when people sort of try to equate that lambda with the vacuum energy quantum expectation from the current best understanding of the standard model of particle physics, there is a factor of 10 to the power 100 or 20 or some discrepancy in terms of the numbers. And this is probably the largest number of, largest factor in discrepancy that we have came across or deal with. What do you think about that?
Absolutely right. I think you pretty much answered your own question, Nirupam. We simply do not know. Absolutely. In my talk, I speculated slightly upon dark matter candidates, and in the discussion earlier about how one can search for it. Dark energy, we really do not understand. And exactly as you say, there is a major difference in scale of what we're discussing here from the energy density.
Yes, Professor Mukhanov. Yeah.
Yes, I think that people sometimes exaggerate their knowledge. Okay, for instance, people were speaking that there is hierarchy problem 10-19 and 10-2. Yeah, because Higgs mass is divergent quadratically. But I am sorry, I always was telling, who told you what is happening beyond the scale which are reached on accelerators? There could be maybe not standard model. There could be variation of the whole thing. But you understand that the whole thing was used, for instance, to push these large extra dimensions, which was a little bit a joke from my point of view, and also supersymmetry, which was much more relevant thing. But supersymmetry was also not completely resolving this problem, as you understand. Therefore, I think people has to be modest and do not make statement telling God how he should act, okay? God acts not on the wishes of the people.
Maybe I can touch on supersymmetry since Professor Mukhanov has raised it.
Yes.
So for those who don't know, this is a theory in which all the particles that I had in my standard model, they all have a partner, a supersymmetric partner with a different property called spin and potentially different masses. But there's a kind of mirror world between everything that I showed and supersymmetric partners. It has some very nice theoretical properties. It has a very nice symmetry in it, which can be powerful for higher level theories, but there is no experimental evidence for it. We have not observed any of these particles. It would be wonderful if the LHC was able to see one of these particles. It would really open up a whole new field. But as of yet, we do not have any experimental evidence for any supersymmetric partners.
Yeah, so we are sort of running short of time. I mean, we are already past our scheduled time, but it has been so exciting. I will come to Professor GuhaThakurta with one more sort of related question. So on one side here is the picture that I get from this discussion, that the initial quantum fluctuations, and as Professor Mukhanov said, if you know this equation, you can work out the entire thing about the universe as a homework or something. I'm sure I cannot. People who have mathematics as their first language probably can work out a lot from those initial things. But then when you look at the details, right, that the details are sort of complicated. So when we want to sort of put things together, there are certain anomalies which come out, for example, the current tension with the Hubble constant, the sigma tension, and so on, which comes from the...
Okay. Let me make comment about disagreement for Hubble constant. Okay, you get the Hubble constant, which is under complete control from CMB measurement. You see, it's real physics. All systematics is under control. You take the Hubble constant from supernova, okay? Supernova, I am sorry, have a lot of systematics. They are not a standard candle, as people believe. Therefore, you should not put all eggs in the same thing. You should never try to please both bad guy and good guy. Instead of that, you have to try to use good guy to learn something about bad guy. In this case, I would take CMB and then would think what you have to do with your theory of standard candles. It's different. It's qualitatively different. People exaggerated this discrepancy, you see? Okay, it's just not comparable.
Yes, I agree. So what I was coming to the question is that, so it involved a lot of complicated baryonic physics, essentially. Things are very uncertain to an extent, which means that making, understanding the observation and interpreting them is not very easy. And you are working on the forefront of that, looking at the detailed, complicated physics of the later part of the evolution of the stars and galaxies, right? Where do you think the next interesting breakthrough result in terms of these complications lies? What will be sort of the forefront in this type of work?
I'm happy to put, make idle predictions here. I'm not going to put any money on it. If I were a betting person, I would be foolish to put any money on this. What we can say with some great certainty is there are missions being planned. The Rubin Observatory, the Roman Telescope. There are missions being planned that are going to open up discovery space. That is something you could say with a fair degree of certainty. What those discoveries are going to be, we don't know. And that's precisely what makes these missions exciting. They're going to open up discovery space because we're going to be able to look at things with greater precision, with smaller and different systematics than before. To me, that's the only certainty. In fact, if you look back at things like the Hubble Space Telescope or the Keck Telescope or the Planck mission, sometimes the biggest discoveries, the most exciting discoveries were precisely the things that weren't exactly predicted. So I think as you pointed out, there's a lot of messiness in the Lambda CDM model that we don't understand. I see that as job security for myself, right? I mean, this is, Chris and Professor Mukhanov, standard model of particle physics is a more complete model. I think that means I have greater job security than you do. The other thing I was going to say is I would never be caught red or dead in a red elliptical galaxy. But I'll die long before our galaxy turns into a red and dead elliptical. Jokes apart, I think it would be. It's really difficult to predict what the greatest, hits will be from astrophysics in the next decade. I think stronger observational constraints on dark energy, on the clumping of dark matter, spatial concentration of dark matter. These are things that one can reasonably expect to measure in the near future.
Okay, so I think it's this discussion has gone for a long time. We have already overshot the time by 10 minutes or so. Maybe I can just quickly take a couple of questions from the audience, and then we can wrap it up in next 5 minutes or so. So one of the questions that we have got is, what is your comment about the fractal nature of the universe? So I don't know who would like to comment on this. Maybe Professor Mukhanov.
What can you repeat question?
About the fractal nature of the universe.
Sorry, I didn't get again.
Fractal?
Fractal universe.
Yeah.
Why should we the fractal universe? You see, the universe which we know right now, we know quite well, even concerning large-scale structure, because you understand that finally, 20 years ago, people managed to make three-dimensional picture of the universe, so-called web-like structure. When you have clusters of galaxies connected with filaments, filaments are connected with walls, and there are voids there. You know that 40 years ago, it was impossible to imagine even this thing. Okay, it was a great progress on the astrophysical side. I recall one astronomer with whom I talked, he was dreaming about getting full sample of 5,000 redshift, you see. Now, Sloan digital survey took millions of the redshift, and you have a great picture of the large-scale distribution. People found baryon acoustic oscillation. I can tell you one more thing, okay? It's not just CMB. If you take Big Bang nucleosynthesis, yeah, which is the other greatest thing, it's the measurement of deuterium made by Max Pettini, okay, at some kind of redshift 2 or 3, they are in so full agreement with CMB determination of the abundance of baryons that it's even amazing. And accuracy which he has is comparable with CMB. You know what is the problem? Why he has twice worse accuracy? Because some reactions are not well measured on the Earth, on this kind of nuclear reactors, you see. Therefore, we know quite a lot about universe. We know quite a lot. We will learn perhaps also something more about developing of this structure, etc., some kind of details. You understand that when kids are growing to become adults, but it's already more on biological side, as I would say. Physics deals with the simplest questions, you see, which are treatable.
Okay, and I have one question for Professor Parks, that we have the gravitational wave and we have the electromagnetic wave. Is there possibility of waves, similar waves for the other two fundamental forces?
So first, maybe let me distinguish between gravitational waves and the other three forces. So gravitational waves are different in that they are a purely classical phenomena. So gravitational waves were discovered only over the last few years. It's a tremendous and very important discovery, and will teach us a lot about the nature of the universe. But it's quite different from the waves that we are talking about in the other three forces, where we look instead at a quantum mechanical phenomena with a particle and wave duality, where you can describe electromagnetic waves, or you can describe a photon, the particle that transmits the electromagnetic force. And the same thing is true for the other two forces, the strong force and the weak force, where again they have particle equivalents which are transmitting them. In the case of the strong force, it's called the gluons. And in the case of the weak force, they're called the W and Z bosons. Now, for gravity, however, we do not have a quantum theory describing that which we can embed in our general fundamental theory. If you could do so, the hypothesis would be that you would be able to have a particle or wave structure for it, and it's known as the graviton. But we have no theory which actually combines a standard model of particle physics, which describes the three forces with gravity. So gravitons would be the hypothesized particle name, and gravitational waves are a purely classical phenomena.
And the final question before we end the session to Professor GuhaThakurta. One of our audience has asked that there are apparently some galaxies which are dark matter deficient. What is your thought on that?
This is a subject of some significant controversy. The measurements are difficult to make. I would say that the jury is still out on that one. I personally have seen a lot of evidence on both sides. Some people claiming that no, there is dark matter, others claiming that no, there isn't. And so I would like to see this settle. And I mean, I think in general, some of the things we were talking about earlier, we were talking about 3 sigma effects. One of the one of the key things here is determining sigma is not easy. That's one of the hardest things to do in experimental science, is knowing what your uncertainty is, especially the systematic component of the uncertainty. The random uncertainties are more easily understandable, but systematic uncertainty is super difficult to pin down. And so something that you thought was a 3 sigma effect might have actually been a 1.5 sigma effect or a 1 sigma effect, but you didn't know what sigma was at the time, right? So
yeah,
I want to say that.
I echo on that it's very important to distinguish between measurements which are statistically dominated and those that are systematically dominated.
certainly.
We were discussing earlier the G-2 and the RK, and those are maybe a little different from each other depending on what your understanding is of the theoretical uncertainties that are involved in them. And indeed, in general, there is more trust on things which are dominated by the statistical uncertainty than when it is dominated by the systematic uncertainty, and you have to make more assumptions.
Sure, yeah. Okay, so I think with that, I mean, we have already sort of overshoot by about 20 minutes or so. We come to the end of this panel discussion. It has been very exciting. I have learned so much from the discussions today, and I would like to really thank you all for being here, taking your time, and joining us in this panel discussion, sharing your thoughts with us. The audience has been, they are asking a lot of questions still, and we are sorry that we cannot really take so many questions because of the finite amount of time we have in hand for this panel discussion. But we strongly encourage you to ask questions. I think that's a very important thing, and there will be avenues to get the answer of your question, even if not from directly through this panel discussion. With that, I once again thank the panelists and allowing me to sort of moderate this session, and I hand it over to Srishti for any final words.
Wow, that was truly an enlightening session. Thank you so much to all the panelists and the moderator for enriching us with your presence and knowledge. Do any of you have any final words for our audience?
Only maybe to you, Srishti, and to Nirupam, many thanks for hosting this very interesting discussion this afternoon.
Thank you so much for being here, sir.
I wanted to echo that. Yeah, thank you, Srishti, thank you, Nirupam, and to the audience. I really admire the wonderful questions that have come out. And just to echo what people have said, science is about asking questions as much as it is about answering questions. So keep asking those questions, keep pursuing your dreams. Nothing is beyond you if you work hard.
Okay. Thank you. Interesting discussion.
Thank you so much for those words.
Thank you, everyone.
Well, this may be the end of the panel. I'm sorry. Yes.
Sorry, Srishti, did you have a different Zoom link for us? I haven't seen something come through in my email.
Yes, I just sent it to you over DM.
Yeah.
Do you want me to say it again?
I've got it. Thank you.
All right. Yes.
Yeah, so
while this may be the end of the panel discussion, it is only the beginning of TechNiche 2021. With many more exciting events to come, here's the most awaited promo for the annual Tech Fest at IIT Guwahati.
Okay, so, okay, good. Is there any other discussion or we finished?
Professor Mukhanov, there is a second link which has been mailed for a Google Meet. We can join there, I think.
I see. Okay, so right now.
Okay. Yes, I'm going to hang up the Zoom call, and I'll take a few minutes before I join the Google Meet, if that's okay.
Yes, sir. Thank you.
Okay,
yes.
Please start without me, though, of course. Don't wait. All right. Thank you. Thank you.
For the audience, this is the promo for Technique 2021.
But now I'll rise above you.
Bye, Srishti. Take care.
Thank you so much for coming, sir.
I'll join
And
the
thank you
other.
all of our audience for participating in today's discussion. Stay tuned for further updates, and links to our social media handles can be found in the chat boxes below. Thank you so much, sir.
All right, take care. I'll see you in the Google Meet.